I'm Jeff Kruk, and I'm a project scientist. And I actually thought maybe I'd just take a minute actually saying what that title means. For small missions that are proposed by an individual team of scientists that's led by a principal investigator, and that's the person responsible. For what NASA calls strategic missions, like Hubble or Webb and so on, this didn't come out of just any one team. These were products of the decadal survey, which in fact is going to talk about on the next slide. This is a process that's been going on in astronomy for 60 years now, where basically once a decade the entire community gets together for about 2 years, writing papers, having town hall meetings, and basically convening panels of senior scientists who devote basically 2 years of their life trying to figure out what their priorities for the next decade should be. And then, so we date back to Hubble in 1972, on up to James Webb, which is going to be launching soon, and then us. And so the science program for these missions come out of the community, not any one group. And so the way NASA manages these things is that there's a project manager who's in charge of running the engineering teams and manages the budget and so on. And they appoint a project scientist who's responsible for making sure that the science program that came out of the decadal survey is what the observatory is actually capable of doing. And so my job is to be the conscience of the project, is to represent the science programs, and I work in very great detail with the engineering teams every time they try to come up with an engineering requirement or they do a trade study. They make sure that what they're doing actually is going to implement the science. Which you might call 4 general categories of science that we're going to address. One is what we call dark energy and the fate of the universe. In the upper left panel there, we show basically 3 schematic views of what the fate of the universe might be. So when I was a lad, the only 2 options people considered were the lower 2 curves there. One where the universe was perfectly balanced between the kinetic energy coming out of the Big Bang and the amount of gravity of all the matter. If that was perfectly balanced, you would just sort of gradually slow down. It's like throwing an apple up in the air at escape velocity from the Earth. It just slows down, but it never actually stops and comes back. Or if there were more matter in the universe than that, it would be like throwing an apple up not fast enough and it comes back, in which case the whole universe comes back in a big crunch. But no one had any vision there might be a third path, which is the upper curve there. And in fact, that's what was discovered in 1998 from type 1a supernovae, that in fact the expansion of the universe is not slowing down, it's speeding up. And so we're going to be studying that in a great more detail, and more besides, which I'll talk about in a minute. More generally, this will be the first opportunity to do wide area surveys in the near infrared. There are probably a couple hundred different science programs that are enabled just by having that capability. And I'll give 1 or 2 examples during the talk. Another thing that came out of the last decadal survey was the recognition that you can find planets around distant stars by gravitational lensing of background stars by the planets. And this is a unique probe that lets you detect planets that are far away from their stars. The Kepler mission and now the TESS mission are capable of finding planets that are very close to their stars, where the planet passes in front of the star to measure how much the light dims. But for planets that are much farther from their host stars than the Earth, each orbit of that planet takes a year, or 5, 10, 20 years. And so your likelihood you'll ever see such an event is too low in the lifetime of the mission. And you still wouldn't believe it until you see many events, because otherwise stars can dim and brighten for other purposes. And so your Kepler and TESS are just not sensitive. With microlensing, you can detect planets anywhere. And then finally, it wasn't envisioned at the time WFIRST was recommended, but one of the other things that decadal survey recommended was develop technologies for high contrast imaging for direct measurements of planets around nearby stars, and that was envisioned for some long-distant future mission. And when NASA acquired a larger telescope for WFIRST, and it became clear that the coronagraph technologies were already advancing enough to be worthwhile, it was decided to put a coronagraph on WFIRST. This is a dating picture of the universe. This one happens to be from Planck. The one from WMAC looks the same. And for present purposes, what's interesting about that figure is that the universe was uniform to essentially 1 part in 10 to the 5 at that time. 1 part in 100,000 was the biggest contrast that existed in the universe. And you look at the universe today, and I thought to count up the orders of magnitude of contrast. Most of the universe is empty space. Galaxies and dark matter are distributed almost like the skin of soap bubbles. Think about a dish full of suds. Most of the suds are just in these very thin films and there's air in between. And that's what the universe looks like. It's mostly empty space with matter distributed in these sheets and filaments. And you get galaxies wherever the density is highest. And so one of the outstanding questions is, how does this process actually work? It's actually governed primarily by dark matter, about which we know nothing other than that it exists because we can measure its gravity. And so we're trying to understand how that whole process turned into stars, people, planets, whatever. So here's a simulation. This is from a science group called the Illustrious Project. If you go to illustriousproject.org, you can pull up all kinds of graphics and videos and so on about the what we know today about the evolution of the structure of the universe. This left column shows the distribution of dark matter going back from 1.5 billion years after the Big Bang up to today at the top. And the key thing to note here is this has already got some structure in it. And as you go forward in time, you get the contrast increases almost exponentially, really. So what you think about, the same process, by the way, happens, as was mentioned earlier, about fragmentation of gas into stars. The same thing happens on the scale of galaxies and clusters of galaxies. You start out with a little bit more matter in one place and a little bit less somewhere else, and gravity just runs its course. The denser parts get denser, and the less dense parts get ever more vacuous, shall we say. This next panel, we won't talk too much about. This is an evolution of gas temperature. Well, even at this point, after the Big Bang, enough galaxies had formed to ionize all the gas between the galaxies in the universe, so it was actually already pretty hot. What you can see is as things condense into ever larger numbers of, so star formation is also increasing as this density goes up. And so as you go forward in time, you have more and more stars turning on, and the gas temperature gets hotter and hotter accordingly. Finally, over in this rightmost panel is what we call metallicity. This is the abundance of everything heavier than hydrogen and helium. Early in the universe, there wasn't much besides hydrogen and helium. But as stars turn on and burn hydrogen and helium to heavier elements, you can see that go up. So one of the new pieces of the puzzle of what the nature of the universe is really didn't become clear until after we discovered the universe, expansion was accelerating, and looking at data from the WMAP and Planck satellites. And now what we know is that all the part of the universe we can see, which is stars, gas, and neutrinos, is only about 5% of the energy density of the universe today. We know that about 27% of it is dark matter, and then the other 68% is the thing that's a completely new force of nature, really. We don't know if it's a variant of gravity, which to my mind is equivalent of a force of nature, or it could be something completely different. And since I started out in life as a physicist, and when this came out, I thought, well, I've got to do something about this, help figure it out. And so I basically abandoned the research I was doing back then and started working on designing this mission. The things we do is by measuring the distribution of galaxies, we can look at the interplay over time with dark matter, which essentially is always an attractive force, so it causes clusters of galaxies to form and form more quickly. And dark energy, which has the opposite effect, it's trying to push matter further and further apart. And one of the things that seems to be apparent is that the energy density of dark matter is effectively always increasing because the contrast of where matter is getting greater and greater. And so in those regions, the energy density of dark matter is increasing. But as the universe expands, this seems to be not changing. So as the universe expands, the energy density of everything else starts to diffuse. The impact of dark energy is getting greater and greater. And so that's why, if you go back to the first slide, you see that top curve growing ever more steeply. And so by looking at the shape of that curve, essentially the geometry of the universe, over the life of the universe, we can tell which one, the relative strengths of the dark matter gravity and the repulsive force of dark energy. So one of the ways we measure the distribution of matter is by gravitational lensing. As you look at some distant galaxy, the path the light takes to get from it to you is deflected. And by looking at, and what that does then is for the light from different parts of the background galaxy get deflected by slightly different amounts. And so what you find is that the shapes of the galaxies that you measure aren't going to be random. They'll actually be correlated by the amount of foreground material you look at. And I meant to bring one of these blocks. If you've ever seen these glass blocks people put in walls for showers that will give you this very wavy view of the background, that's exactly what happens to light from background galaxies as it passes through all the material between us and it, which is mostly dark matter. It gets deflected and distorted, and those deflections and distortions are correlated over some size scale, because that's, the size scale is determined by what the mass is that you're passing through. So by measuring the distribution, the correlations of the shapes of galaxies over a wide area, you can reconstruct the distribution of matter in between. There have been a few programs on Hubble to do this, mostly looking at just clusters of galaxies. They don't have the field of view to do it on large scales, and that's why you need a mission like WFIRST. Now to go back to the one of the other techniques we use, and this is, so the weak lensing is giving us the distribution of dark matter as a function of time. So that's one of the techniques we'll be using to study the structure of the universe. The next technique is to actually just measure galaxies directly, as opposed to measuring the distortions of their images by background light. So here's a picture taken by Hubble of one very tiny part of the sky. And we will be taking images like this over a larger region. We'll also be putting what we call a prism in the beam, or like a prism, where we'll get a spectrum of every object in the field of view. So we'll be measuring the two-dimensional positions of galaxies from the image, and we'll be measuring the redshift of all the images. So that gives us the three-dimensional distribution of galaxies as a function of redshift. So here's just one example of how this works from Hubble. There's this one image of a galaxy up here. They use two prisms to get the spectrum. And when you, so you have an emission line like this, what you'll see is a bright spot in the spectrum. So this particular galaxy has 4 lines, 3 that we measured in that prism, 1 from here. And once you've got a few lines, you can figure out what they are, and that's how you measure the redshift. Then finally, there's our third technique for measuring the expansion history of the universe. This was the one that was used to determine that it was accelerating in the first place, and that's to look at type 1a supernovae. Unlike the standard ruler of the variations left over from the Big Bang, supernovae are what we call standard candles. This type of supernova is thought to be a standard candle because they are thought to be the product of a star, of a white dwarf that hits the Chandrasekhar limit, which is always the same mass. The same mass for all such supernovae. When you exceed that mass, the star just collapses. The entire star burns up in a thermonuclear explosion, and you get, for a few days, something that's brighter than an entire galaxy. So the key, there have been several hundred of these measured from the ground, a few by Hubble, but those are all limited to very low redshifts. If you want to use this technique to study things at much higher redshift, you have to go into space and work in the near infrared. And if you look, you can see sometimes the supernova is way out away from the center of the galaxy. It's very easy to measure. Other times, it's essentially right on top of the center. And so you need an observatory with resolution like Hubble in order to be able to make sense of the data. And so that's what we have with WFIRST. The advantage of WFIRST over Hubble is simply the field of view. As I'll talk a little bit more later, we have essentially 100 times the field of view of the Hubble Space Telescope. And so essentially wherever we point, there will probably always be at least one supernova in the process of going off. So you could do this experiment with Hubble. In fact, I get occasionally asked by people at NASA headquarters why we can't do it with Hubble or with Webb, and the answer is it would take you 500 years. You could do it, but it's just not efficient. So what we do with, to characterize a supernova is you measure its light curve in different filters. So this happens to be ground-based data, but supernova in the ultraviolet goes up, and then it declines very quickly. As you go out into blue wavelengths, it declines a little more slowly, and so on. When you get out into the red and infrared, you actually have another process going on. These early, these blue wavelengths is driven by radioactive decay of the elements created in the explosion itself. But then in the infrared, what you see happening is actually light that's reprocessed in the ejecta. As the ejecta cools, the opacity changes at different wavelengths. You actually get a second peak in the light curve. And you can use this actually as a good identifier for the right type of supernovae. The brightness is very well understood. And again, we're only trying to measure, since you're measuring the same type of supernova over cosmic time, it's really just the relative brightnesses you need to measure well. So that gives you the distance. And then what the redshift gives you from the spectrum, you can measure the redshift. You know what each of these absorption features are. That then tells you the velocity at which the universe was expanding at that point in its history. It's that combination of the distances and the velocities that lets you reconstruct the expansion history. The three probes I was just talking about for determining the growth of structure in the universe from the earliest days until now. The expansion history that we get both from the three-dimensional distribution of galaxies and from type 1A supernovae. This is how we hope to unravel the mystery of what dark energy is, what dark matter is, and whether or not we need to modify gravity. This is just shows how the different probes we have operate as either a function of redshift over here or as a function of cosmic time. We basically start looking at objects that were created only 2.2 billion years after the Big Bang, all the way up today. But the point I wanted to make about this plot is that over most of cosmic time, the universe really was slowing down, just like we all thought it would have to do. It was right around 4.5, 5 billion years ago, which in fact is about the time the solar system was formed. They're not connected, but it's a good yardstick to think about. And then the universe started speeding up. And the shape of this curve is one of the things we are trying to measure, because that will be the thing you then compare against different models of what gravity might be doing. Let me turn my attention now to one of the other programs, which is Gravitational Microlensing for detecting planets. One thing you probably don't think about from as amateurs observing the sky is that all the stars are moving all the time. And if you look at a dense field, like the center of the galaxy, there's a reasonable chance that stars will line up, almost exactly. And so what happens then, if you're sitting here, whether you're on an observatory on the ground, or looking at an observatory in space, and you're looking at some background star, eventually it's about a 1 part per million chance, this will happen for any one star, they will line up. And so what happens then is that the light from the background star gets deflected and magnified by the foreground star. This is something that's actually been measured many, many times. But the interesting thing is that the planet will do the same thing. And so what you'll find, as you, this is intended to be a progression of the intensity of the background star. It starts to go up as it approaches being lined up the foreground star. This time scale for the two stars to line up, given the typical motions of a galactic rotation, is like a month or two. But because the planet is so much less massive than the star, the time scale for magnification by the planet is like a day. For a really low mass planet like Mars, it might be a few hours. For Jupiter, it might be a couple days. So you have this characteristic light curve where you get this nice broad bump in magnification that lasts a month or two, and then you get these little spikes. And by observing a lot of planets, by observing a lot of stars, you can actually find planets in a reasonable cadence. So I said a minute ago that the likelihood of a lineup being close enough is about 1 in a million. But if you look at the center of the galaxy, you've got, we'll be monitoring about 2 billion stars on a 15-minute cadence. And so that means over the course of a year, you'll have a couple thousand planet detections. And so it's actually a very efficient way of characterizing planets. Here's a graphic trying to show how this looks like. You've got here on the lower right a star with a planet, and then as the galaxy rotates, they start to line up with a background star. And what you then start seeing, over here we've got the figure showing what happens to the light rays, and over on the left is what the light curve looks like with a sharp blip caused by the planet and a much broader one caused by the star. This is what such an event looks like for a Jupiter-mass planet. This is all data taken from the ground. The total span here is about 200 days. And this great big broad peak are the two stars lining up. And then this sharp peak over here is the amplification caused by the planet. And interestingly, you have to look really close, there's also a little blip where you get the same sort of event happening on the other side of the passage, but because now the things don't line up quite so well, the peak's much smaller. But by having both those blips, that tells you something about the geometry of the planetary system. You can start deriving the orbit size of the planet. And then, if you can determine the spectral type of the star, so you know the star's mass, then you can derive the planet's mass too. So you need very high precision measurements, because all those things you derive come out of asymmetries in the shapes of these light curves. It's very difficult to get that kind of precision from the ground. Here they did it because it was a very bright star and it was a very massive planet. But if you want to go to small planets, you've got to do that from space. Here's a model. The last figure was real data. This is a simulation of what would happen with an Earth-mass planet. The interesting thing here is that the magnification is still very large. But the difference between an Earth-mass planet and a Jupiter-mass planet is that now the event is only a few hours. So you have to be observing your star pretty rapidly in order to get enough points on that curve. And that's another reason why you need a large field of view. It's one reason why your observatory has to be agile. You have to go smooth and settled over the next place really quickly, so you can come back and measure a lot of different places and get enough points on these curves. So this is what the distribution of planets might look like. The blue points over here are actual detections from Kepler. The plot is the orbit radius, so 1 astronomical unit is orbit of the Earth. So you can see Kepler has some detections out to about 1 AU, and really nothing much beyond there. And then the other axis is planet mass. The test satellite is actually going to be restricted to orbit radii of probably 0.1, maybe 0.2 AU, something like that. So they will find a lot of planets. They will find them close to us, but they will all be very close to their stars. With WFIRST, it's almost the exact opposite. We're most sensitive at larger radii. When you think about a solar system, most of the area is out at large radii. So we really have no insight into what's going on in other stellar systems from Kepler or TESS. We do know from Kepler that most solar systems are not like ours. They're finding gazillion planets really close. But, nothing like what we have in our solar system. So it just really makes you wonder what's going on in the outer reaches of all those. The other thing doesn't show up here. With microlensing, you can also detect planets that are not attached to stars. There have been 2 such detected. I think it's just 2 from the ground. So there's a lot of very lonely, very cold planets out there, and we'll be able to measure those as well. So let me say a few words now about the coronagraph. So the problem of directly imaging another planet around a nearby star, okay, it's basically like trying to see a firefly next to a spotlight in LA from here. That's like the contrast ratio you have to achieve. And then, and that's for like a Jupiter-mass planet. If you want to observe an Earth-like planet, which is what we want to do, that's like seeing a firefly next to 1,000 spotlights. So I mean, this is hard. The key thing that the WFIRST coronagraph is supposed to do is actually advance the state of the technology in a whole range of areas. And the thing that's missing over here is closed-loop control of the wavefront sensing. If you look at the coronagraphs that have flown on Hubble or they're flying on the Webb, it's just a simple occulting mask and the focal plane. And you can get contrast of about a part in a million that way, which is pretty good, but you really need to get to a part in a billion to a part in 10 billion to start seeing most planets. And so what we'll be doing on WFIRST is actually sensing all the imperfections in the optics, computing what kind of corrections to apply to deformable mirrors. That's actually a computationally intensive thing. Things have been attempted on the ground. There's only so far you can get with the atmosphere. In space, you really expect to get several orders of magnitude improvement. Another thing we'll be doing is developing completely new kinds of masks for controlling diffraction. It actually is possible to beat the diffraction limit if you're very careful in what you do. Another thing we'll be doing is developing detectors that are essentially zero read noise. This is important because planets are essentially 30th magnitude. You get an occasional photon every now and then. If you have even a few electrons read noise, you're doomed. So it's another thing that we'll be demonstrating on WFIRST. And then finally, there's very clever techniques for post-processing. Even after you do some work on controlling diffraction, you can't get rid of all of it. You have all these interference patterns called speckles. But you can characterize those, and if you're careful about it, you can get rid of most of those. And you can actually then pull a planet out here that you would never have been able to pull out there. And that's just from being clever in how you take the data and how you process it. There's the deformable mirror we've been working on, and there's a test bed that we've been testing all this out on at JPL. So you have light coming in from your telescope, and at this point you have quite a few different feedback loops. We have a fast steering mirror so that we can take out any small jitter, even in space. There's jitter of a few really arc seconds to deal with, even with Hubble class type observatory. Here are the deformable mirrors I talked about. The way those work is you examine features in your final camera or in your spectrograph that we have. You feed this back into a control loop, and you adjust these deformable mirrors. It takes you a few hours actually to go through this, even when you're looking at a bright star. You have to collect a lot of photons to characterize all the different ways your optics can be slightly deformed. But we've got this working very nicely in the lab. And then you have a whole series of masks for controlling diffraction, controlling stray light. We actually have 2 completely different architectures for doing that. And the end result, when you come out, is so far in the lab, we're achieving basically 1 part per billion contrast. So we're already in the lab doing about a factor of 1,000 better than with Hubble. And we see no reason why that we shouldn't be able to continue with that performance when we get into space. So filters, so on these polarizers for looking at things like dust and debris disks, where a lot of the light coming off the disks around the stars is polarized, and so let us help characterize properties of those disks. That's actually a very promising aspect of the science. These are we use for looking at systems that have not yet formed planets. So it will help us test theories of planet formation. Here's a simulation of what a system would look like around one of the nearby stars that I'm thinking about observing. This has got both dust. This would be like there's a diagonal cloud in our solar system, along with some planets. This is sort of one of our tests to show that given the expected properties of what we know about other planetary systems and what we know about the properties of the instrument, will it actually all work and fit together? So here's a figure on the right showing our expected performance and the performance of present instruments. So up here is the NICMOS coronagraph on Hubble, predicted performance for the coronagraph on Webb. Here's the state-of-the-art ground-based coronagraph on the Gemini observatory. And these are all giving a contrast of 10 to the minus 5, 10 to the minus 6. These curves down here are our predicted performance for WFIRST. And all of these triangles are planets known to exist from radial velocity measurements. And so even though we're still just a technology demonstration instrument, the capabilities appear to be plenty good enough to be studying planets we already know. And so we ought to have a very successful observing program. Let me just give a couple of examples, more concrete examples about the benefits of wide field we have on WFIRST. Here is basically 1/4 of Andromeda that's been observed with Hubble. And this is what the tiling pattern on Hubble was to do that. It was over 400 separate pointings. It took a very long time. And on WFIRST, you can do it in essentially 1.5 pointings. So it's an enormous gain in speed. And one of the programs for Andromeda was to try to measure the characteristics of every star. You find galaxies don't just have one kind of star or one population of stars. Galaxies are assembled by gathering up other galaxies. So a big galaxy like Andromeda or the Milky Way started out as a modest-sized galaxy. And then it started acquiring all the nearby smaller galaxies. Those smaller galaxies evolved more slowly. They have much lower metallicity. There's a lot more gas. The gas-to-star ratio is different. And so if you look at a big galaxy, you can actually see all these different pieces. The properties vary across the galaxy, different places. The halos might have different constituents. So here's just sort of a simulation from one nearby galaxy that we've been studying for simulation purposes, where we generate fake stellar populations. Some of this has been done with Hubble, not just with Andromeda, 1 or 2 others. And if you take a galaxy, this one is, this one's M83. We actually have Hubble data in a few spots in the distant halo of this. And when you look at the stellar population in the halos, they're all different compared to what's in the center of the galaxy. And so we plan to be doing this on WFIRST for essentially every nearby galaxy and try to measure the assembly history of all those galaxies. How did they actually come to be? Example of why we call this 100 Hubbles for the 2020s. It's not just that we have a large field of view. They're also designed to be very, very efficient. We move rapidly, we can settle quickly, and there's no Earth in the way. Hubble, you're lucky if you get half of every orbit you can actually observe, because otherwise you have to wait for the Earth to get out of the way. And so you start adding up all these factors. And I just took a couple of really big, iconic Hubble programs, took total calendar time it did take them to do it with Hubble, and how fast we could do it with WFIRST if we wanted to repeat it. And the factors are like 730, 110, 1,000, almost 1,500. So this is really a qualitative difference. This is the thing that separates WFIRST from all the other missions NASA's been doing. I'm going to say a few words about the observatory. This is the present design. Telescope is up just behind this outer barrel assembly here, the top half. There's a fixed solar array, sun shield we call it. Unlike Hubble, it's not on gimbals, it's just fixed. That's one of the key parts of being able to slew and settle rapidly. If we had big gimbaled arrays like Hubble, there's no way we could settle in 10 seconds after a big slew. It would be many minutes. And when you're trying to survey thousands of square degrees of sky, even with a big field, you have hundreds of thousands of maneuvers over the space of a couple of years. If you add a minute or two to every one of those, you spend all your time slewing and settling. So we put a lot of effort into making the observatory very stiff. The instruments are underneath the telescope, and then underneath that, it's a spacecraft bus. We'll be at Sun Earth L2. We generate 11 terabits of data a day, which is a lot to get down to the ground from that far away. Mission duration is 5 years. Consumables, the only consumable is fuel, sized for 10 years, and it is designed to be serviceable. Right now there's no facility to do servicing, but if there is one, we could be serviced. This is just what the inside looks like. In some ways the arrangement's very similar to Hubble, with the telescope up top, instruments underneath, with pick-off mirrors feeding the optical assembly. This is what we call the field of regard. The white region is the part of the sky we can point to at any given instant in time. The main thing is we can't point closer to the sun than 54 degrees or 54 degrees the other way, and that's just because the solar rays are fixed. Otherwise, we can see everything is about 60% of the sky. So for things we need to observe continuously, like supernovae, they'll be pointed up here. We can always get to them. The galactic bulge, can't do anything about it. As was noted earlier, it's like basically right in the ecliptic. So whenever it's not behind the sun or too far away, we can observe it. So that was one of the things that drove the size of the solar arrays. Just says a few words about the instrument. It's wide-field instrument's got a little over a quarter of a square degree field with 0.1 arc-second pixels. We have filters from a half a micron up to 2 microns, and slit spectroscopy from potentially 1 to 2 microns. And this is to answer your question. This is what the orbit looks like. The top view is up here, the Earth and the Moon. It's good to see the orbit of the Moon, because it's actually roughly similar in size to what the actual size of our orbit is going to be. You tend to think of Lagrange points as just points in space, but they're not. It's a pretty wide neighborhood. If you look at the gravitational potential, it's very, very flat out here. You can get around in here with very little expenditure of fuel. And this is from looking out from the sun, looking outwards. And so there's the Earth, and then behind it is this semi-halo orbit. And the point is, it really is tilted. It's raised a little bit out of the plane of the ecliptic. It's not just perpendicular to it. And that's arranged primarily so that it never gets too far north or too far south. Because if it did, then you couldn't see it from a ground station antenna in the northern hemisphere. Or conversely, when the observatory was north, you couldn't see it from one in the southern hemisphere. So we try not to let it get too far out of the plane so that we have reasonable contact times from several ground stations. Here we are in the middle of Phase B. The formal project really started in FY13, launches in 2025, so we're actually almost exactly halfway to launch from when we started. We're fairly far along. I just wanted to say a few words about what these phases are that are on the previous chart. I've tried to really boil it down for my scientist friends, because frankly, if you read the NASA documents, they're pretty opaque. But in phase A, this is a little glib, but phase A, you decide what the mission does. And this sounds simple until you write the several hundred pages of requirements documents that actually specify in exquisite detail what it is the mission does. It took us several years to do that. And at first it seems trivial, and then you start figuring out other things. You have someone who didn't write it, read it, and say, what about that, what about that? That's ambiguous. And you go back and you do it over and over and over. You start figuring out what's really hard, and you go back to the engineers. Is there a way around this? And you go back to the science team. Is there a different way to do this? And so that was what that whole process was. Phase B, this is what we did in the design down to almost the last nut and bolt. You are still allowed to, and in fact they call phase C detailed design, but at that point you actually are changing almost nothing. That's when you've got the last few trade studies that maybe you haven't finished quite earlier, but in phase C, really, that's when you actually build it. Phase D is when you put it all together and you test it. And testing it is not just making sure it works. This is when you put it through vibration testing, thermal vacuum testing, end-to-end performance testing, whatever. And then finally is the fun part, to take data. So a few other words about where we are. You've probably heard that we acquired a telescope from another government agency. There it is. We're actually allowed to take pictures. This was actually about a year ago. Since then, it's actually been completely taken apart. We're changing the optical prescription slightly. That mirror is now in a big chamber going through what we call ion figuring. We're going to remove about a micron off the surface to change the prescription very slightly. We finished the first round of that last month. It's going back for the next of several rounds. So what we inherited were the first two mirrors of a TMA whose final parameters we don't know. And we're adapting it to us. We're building a new tertiary. And then on the left here is one of our prototype detectors. These are new. It's a 4K by 4K mercury cadmium telluride detector, 10 micron pixels. We've had these under development for most of a decade now. We've completely finished all the prototypes. This one is a prototype. We actually got that one several years ago. And we've started fabrication of the flight detectors. The first flight detectors are coming in a couple weeks. They're on track, actually, for launch in fall 2025. All the observing time gets selected competitively, and all the data is going to be public. You can log into the archive and get data yourself. Basically, I think our requirement is within 3 days of downlink, it has to be out to the public. And the main thing about the archive is that with Hubble, the real legacy is the archive. Already today, in any given year, more papers are published out of archival data than from data taken the year before. And so, our archive is going to be just vast. And in fact, probably one of the harder parts of the mission is not any of the technical things we just talked about, but figure out how you're actually going to use all that data. It's, you can't just look at it. Right? You can look at any little piece, but all of it, there's just no way. And it's figuring out how to do that in an intelligent way is one of the things we're grappling with.